In Lecture 7, we'll spend some time comparing methods to track spontaneity or the non-spontaneity of redox reactions. We'll spend maybe the first 4 or so slides on that, and then we'll end up discussing a topic called electrical work. If you recall earlier in this module, in Lecture 3, we saw that for a redox reaction, there was a direct relationship between the standard potential and the free energy change. It was written here as delta G equals minus NFE. In addition, in Module 7, we discussed the relationship between the free energy change and the equilibrium constant for a reaction. Therefore, for a redox reaction, the quantities delta G and E0 and K can be easily interconverted, and each quantity is a way of expressing the extent of reaction spontaneity or non-spontaneity. Many times in general chemistry textbooks, you'll see a diagram similar to this, constructed as kind of a triangle, and in between the vertices of this triangle is a relationship, that mathematical relationship between two adjacent vertices of the triangle. So simply stated, between delta G and K, there's a relationship here. Between E0 and delta G, the relationship is right here. There's also a relationship between the standard potential E0 and the equilibrium constant. This equation is easily derived from the other two. We can do it quickly here. If delta G equals minus NFE and delta G equals minus RT ln of K, then minus NFE equals minus RT ln of K. And if we simply solve for E, we'd end up with RT over NF times the natural log of the equilibrium constant. Let's look at an example problem on the next slide. Well, let's look at this reaction here, which is a redox reaction that involves the oxidation of cobalt-2 to cobalt-3 by oxygen in an acidic environment. And what the question asks us to do is to calculate the magnitudes and signs of the standard potential E, the free energy change, and the magnitude of the equilibrium constant for this reaction. And as I said, what we're basically asking is whether or not oxygen is capable of oxidizing cobalt-2 to cobalt-3 in an acidic solution. So if we end up with a negative potential, a positive delta G, and a small equilibrium constant, hint, hint, we'll find out that oxygen is not capable of oxidizing cobalt-2 to cobalt-3. Now that I've spoiled the end, let's see how we get there. So following the directions here, let's first determine the standard potential. As you recall, there's 2 ways we could do this, and just for completeness here and maybe a little review, we'll illustrate both methods. So let's assign oxidation numbers to this balanced redox equation. And of course, the oxidation number of cobalt-2 plus is +2, of oxygen is 0 because it's elemental oxygen. Hydrogen ion would be +1. Cobalt-3, of course, would be +3. Hydrogen in water is +1, and oxygen in water is -2. And we can write out the relevant half reactions. The relevant half reactions would be cobalt-3 plus 1 electron going to cobalt-2. And you might ask, now wait a minute, that's not the half reaction that we're talking about here, because if we're going from left to right, the half reaction would be cobalt-2 going to cobalt-3, and you are correct. But what I really wanted to do here was just find the relevant half reaction in the table of standard reduction potentials. If you have the table in front of you, you'd find a half reaction. Remember, they're all written as reductions of cobalt-3 plus 1 electron going to cobalt-2. So what I found is the relevant reduction in the table of standard reductions that relates cobalt-3 and cobalt-2, and the reduction potential on that table is plus 1.842 volts. If I find the redox reaction relevant for oxygen that involves oxygen, 4 hydrogen ions, and 2 water molecules, this is what you'd find on the table of standard reduction potentials. And the E0 value read off the table is plus 1.23 volts. So now what we're going to do here is write out the actual oxidation half reaction from this overall reaction and the reduction half reaction. So if we do that, you can see that, of course, 4 cobalt-2 pluses are going to 4 cobalt-3 pluses plus 4 electrons, because that's how many you'd count in this process. And since we're reversing the reduction that's written in the table of standard reduction potentials, we're going to reverse the sign of E0. So that would be minus 1.842 volts. We can now just write out the reduction of oxygen right off the table because it suits adding together with this equation to give the overall equation. Anyway, we're going to have 1.23 volts from that. And of course, now we write the overall reaction. So these two will add up to our overall target reaction. And of course, what we do is add these two potentials together, and we get an overall potential for this reaction of minus 0.61 volts. So from using voltages from the table of standard reduction potentials, we see that the overall potential for this reaction is negative, which predicts that the reaction should not be spontaneous, but we'll keep going here. Now, I had said before we'd, for review, compare our two methods for getting E0. Remember, we can just use this formula. The overall E cell, or the E of the reaction, is equal to the reduction potential that you read right off the table for the cathode and the reduction potential for the anode, just reading the values right off the table. So we'd have 1.23 volts and minus 1.842 volts, which would give us, again, minus 0.61 volts as the overall potential for this reaction. And again, since E0 for the overall reaction is negative, the reaction as written, left to right, is not spontaneous. That is, we do not expect oxygen to be able to oxidize cobalt-2 plus to cobalt-3 plus in an acidic aqueous solution. Of course, we also expect delta G to be positive now and K to be very small. Let's calculate those on the next slide. So continuing our example from the previous slide, let's go ahead and calculate delta G. As you can see and recall from the first slide, that delta G equals minus NFE, N being, of course, the number of moles of electrons in the balanced reaction as written, times Faraday's constant, times the voltage, joules per coulomb for volts. When the units cancel and we change over to kilojoules, we get a delta G, a standard delta G of 240 kilojoules. So delta G is large and it's quite positive. And as we already know from the E0 value, this reaction is quite non-spontaneous. Well, let's just hold up a minute here and recall from lecture 4 in module 7, we talked about the fact that thermodynamic quantities like delta G are often reported on a per mole of reaction basis. So we could report this result here as 2.4 times 10 to the second kilojoules per mole. And you might ask, well, could we get this result from the above equation without having to simply insert per mole in the answer? In other words, can we get it per mole to fall out when we cancel out units and not just add it at the end? And I just want to point out that yes, we can if we're a little bit more honest about the unit analysis here. So let me show you what I mean. You'll notice I'm rewriting our calculation for delta G down here. And what I've added is that, to be honest, the 4 moles of electrons is the number of moles of electrons transferred per mole of reaction. And that's correct. So now we can cancel out the moles of electrons because Faraday's constant is coulombs per mole of electrons. So we cancel that out, and of course cancel out coulombs. And we end up with joules per mole of reaction, or kilojoules per mole of reaction. Now, interestingly, I have found that some general chemistry textbooks deal with this by simply using the number of moles of electrons transferred as a unitless quantity and simply pretending that the moles of electrons in Faraday's constant is actually moles of reaction. Thus, you could rewrite this calculation again, and you might see me do this in the future, putting a unitless number in here for the number of moles of electrons transferred, and instead of writing moles of electrons for Faraday's constant, just writing per mole. And if we do that, we get kilojoules per mole, and no one knows the difference, or at least you don't unless you look at it a little more closely. So let's go on to calculate K for this redox reaction. Well, here's our reaction. We've calculated E0. We've calculated the free energy change. Now let's calculate K. Remember from slide 1 that the standard potential equals RT over NF times the natural log of K. So if we solve for the natural log of K, we can do that by cross multiplying E0 and NF and dividing by RT, filling in the numbers. And remember here, I'm just following what you see fairly often in textbooks and just use the number of moles transferred as a unitless number and use just moles of reaction here for Faraday's constant. And of course now the moles cancel out, and Kelvin, degrees Kelvin cancel out, joules cancel out, coulombs cancel out, and we get this unitless number, which we should for the natural log of K. If we now solve for K, we can do that by taking e to the power of ln of K and e to the minus 95.02, which means we'd get K equals e to the minus 95.02. K is now an incredibly small number, which again indicates that the reaction is quite non-spontaneous and is consistent with the negative E0 and the positive delta G. So if we summarize here, we'd say that for this redox reaction as written from left to right, the E0 is negative, delta G is positive, K is ridiculously small. All of these are consistent with a reaction that is non-spontaneous. So as we've said before, we would predict that cobalt-2 will not be oxidized to cobalt-3 by oxygen in an acidic solution. Now, as promised at the beginning, I said we'll spend a few slides talking about electrical work. And if we recall in the last slide of Lecture 5 and Module 7, we introduced, kind of as an extra at the end, the equation that free energy change equals W max. And we noted at the time that if delta G is negative, W max would be negative, and W max would represent the maximum useful work available from a spontaneous reaction. If delta G was positive, W max, of course, would be positive, and it would represent the minimum work needed to get a non-spontaneous reaction to proceed. As noted in the previous slides, the standard free energy change equals minus N times F times a standard potential. That would also mean that the free energy change under non-standard conditions would equal minus NFE, E being under non-standard conditions, and non-standard conditions are pretty much what we see all the time. Therefore, if this is true, we could now write the equation that W max equals minus NFE. And it's perfectly valid to ask what's the point here, and we'll try to defend this. If we know the voltage generated by a battery, a voltaic cell, we can calculate the maximum work output from this battery to power whatever device you think is important to power. For electrolysis, if we know the voltage of the electrical current we are applying, we can calculate the minimum work needed to drive an important chemical reaction, such as the Hall Héroult process for the production of aluminum metal. So let's examine these 2 points one at a time. So let's tackle number 1. If we know the voltage generated by a battery, a voltaic cell, we can calculate the maximum work output from this battery to power your device, whichever you think is important to power at the time. So let's suppose we had a 1.5 volt battery, such as an alkaline AA battery, where the anode was zinc metal. Using the appropriate equation above, we could calculate the maximum work in kilojoules that we can expect from this battery. So let's do that calculation. The maximum useful work would be minus NFE. Now for a battery based on zinc, N would be 2, because remember the half reaction at the anode would be zinc metal going to zinc 2 plus 2 electrons. If we put that 2 into our equation minus NFE, for E we're using 1.5 volts or 1.5 joules per coulomb. We use the Faraday's constant. We'd get minus 290 kilojoules per mole. Now the minus sign simply means that the system, in this case the battery, would do work on the surroundings, meaning power a device. So we'll try to get a handle on this result of minus 290 kilojoules per mole on the next slide. So as we just said, we calculated we can expect to get a maximum of 290 kilojoules of work. I left off the minus sign here, it's just semantics, from a typical 1.5 volt AA battery where the anode material was zinc metal. And we use this equation and of course got minus 290 kilojoules per mole, because again the battery is the system doing work on the surroundings on your device, so if mathematically it would have a minus sign. And now we might want to think about what this 2 means here. You say, well, it means, remember, 2 moles of electrons. Well, that's fine. We use it as a unitless number, that's fine. But if it really is 2 moles of electrons, it implies that our battery has 1 mole of zinc metal, or 65.38 grams in your AA battery. So again, if we're implying we're getting 2 moles of electrons, we must be getting those 2 moles of electrons from a mole of zinc atoms going to zinc 2 plus ions. Well, there's a little bit of a problem there in that the typical AA battery has a total mass of about 24 grams. So clearly there's not 1 mole of zinc metal, 65.38 grams, in one AA battery. So if we make that assumption that the battery is 24 grams, and then we make another assumption that the battery is about 25% zinc metal, then the mass of zinc in each battery would be about 6 grams. So what I'm going to do is I'm going to scale down how much work we would expect to get out of our battery by about 90%. So we'll only get about 1/10 of what we think because we only have about 1/10 of a mole. If I calculate how many moles of zinc are in 6 grams, we get something close to 1/10, 0.092 moles per AA battery. And then I'll adjust our previous calculation of W max. So we say if we get minus 290 kilojoules out of a mole of zinc, but we only have 0.092 moles of zinc, then we'd get about minus 27 kilojoules of work out of our AA battery. So this is our estimate of the total energy available from one typical AA battery. This, of course, assumes that the voltage stays constant at 1.5 volts for the entire life of the battery, which it does not, but we will not concern ourselves with that additional complication at this point. So, what can we do with 27 kilojoules of energy from a AA battery? Well, your instructor's wireless mouse that he's now using to do this with the arrow appears to draw an average about 6.5 milliwatts of power. Power is the rate at which energy is consumed. And a milliwatt is 1,000th of a watt. And this 1,000th of a watt, or a milliwatt, is equivalent to 0.001 joules per second. A watt is a joule per second, so 1 watt is the rate of energy use of 1 joule per second, so 0.001 watts would be 0.001 joules per second. So what I'm going to do is calculate, using this information, how much time 27 kilojoules of energy from our AA battery would give us at a rate of energy use of 6.5 milliwatts, which would be 0.0065 joules per second. The way I'm going to do this is I'm going to say 27 kilojoules times the fact that there's 1,000 joules in a kilojoule times the fact that it takes 1 second to use 0.0065 joules at that power rating, gives us 4.15 times 10 to the 6 seconds of time. I dropped the minus sign here on the work just to avoid getting negative time. If we convert this many seconds to hours, it turns out to be about 1,200 hours. And that seems like a lot, and it's only an approximation, but it does seem to be a pretty good reflection of how rarely I need to change the AA battery in this wireless mouse on my desktop computer. So we're examining the equation W max equals minus NFE, and we had 2 points to make about this. First was, if you know the voltage generated by a battery, we could calculate the maximum work output from the battery to power a device. That's what we just did on the previous slide. Let's briefly spend some time on the second point regarding this equation. For electrolysis, which of course is where you have an input of electrical energy to drive what you know is a non-spontaneous reaction for a particular purpose. If you know the voltage of the electrical current that you need to apply to get that reaction to go, you can calculate the minimum work needed to drive this reaction. And as an example, we're going to look at the production of aluminum metal. Now, recall when we discussed this process, which was called the Hall Héroult process, the overall voltage required for the electrolytic production of aluminum was about 4 volts. So what we'd like to do is calculate the minimum work needed to drive the production of a kilogram of aluminum metal. That would be about 2.2 pounds. If you recall that to do this, what we're going to have to do is we're going to have to reduce aluminum 3+ ions to aluminum metal. So we're going to need 3 moles of electrons for every 1 mole of aluminum. If we use our equation W max equals minus NFE, we put in a 3 for the number of electrons that we need. That, remember, that would be 3 moles of electrons. And that would be the number of moles of electrons required to get 1 mole of aluminum. And we put in minus 4 volts, or minus 4 joules per coulomb for E. And we'll use that minus sign because what we're doing here is driving this non-spontaneous reaction. So a non-spontaneous reaction would have a negative potential. If we do that, we get a W max of 1.2 times 10 to the third kilojoules per mole. And we can say that this is per mole of aluminum produced, since 1 mole of aluminum metal is produced for each mole of reaction, in this case, for every 3 moles of electrons that are transferred. So let's just adjust our W max from 1 mole of aluminum to a kilogram of aluminum. We can do that by taking 1.2 times 10 to the third kilojoules per mole of aluminum and multiplying by the fact that 1 mole of aluminum is 26.982 grams of aluminum. At this point, we'd have kilojoules per gram of aluminum, and then multiply by 1,000 grams of aluminum. And what we'd get is a number which would basically be the energy required to produce a kilogram of aluminum. And this would be, of course, the energy that we would require from the electrical input that's going to drive this electrolysis. So production of aluminum by the Hall Héroult process is a pretty complex chemical engineering problem. So energy is not only needed for the electrolysis, which is what we just calculated here for the energy needed to produce a mole of aluminum metal, but you also need energy for maintaining high temperatures and the continuous production of replacement carbon anodes, because remember, they slowly disappear during the electrolysis. That's somewhat dated, but what I found to be still a very useful summary of the electrochemical and engineering details of aluminum production can be found in an article in Journal of Chemical Education from 1983. This author supplies a simple equation to estimate the electrical energy cost in the energy units kilowatt hours. Those units are commonly seen on a household electricity bill. And the equation looks like this: the number of kilowatt hours of energy required to produce 1 kilogram of aluminum equals 298.06 times the voltage drop in the cell divided by the percent current efficiency. The percent current efficiency is estimated to be about 90%. And if we use the voltage drop 4 volts, we can get a energy requirement to produce a kilogram of aluminum. And I assume this means for the entire process, not just the production of aluminum from aluminum 3 plus, but also running the plant, maintaining the high temperatures, production of carbon anodes, and so forth. And using this author's simple equation, I get about 13 kilowatt hours to produce a kilogram, about 2.2 pounds of aluminum metal. So you might ask, well, is this a big deal? Because after all, if you look on a power bill that you would get at your home or apartment, the average US household apparently uses about 900 kilowatt hours of electrical energy every month. So you'd look at this and think, well, I guess 13 kilowatt hours to produce a kilogram of aluminum doesn't seem like a lot. Well, the world needs a lot of aluminum metal. In 2010, according to a reference that I found, worldwide production of aluminum metal was around 4.1 times 10 to the 10th kilograms. That's a lot of kilograms of aluminum. So if I just take 4.1 times 10 to the 10th kilograms of aluminum and multiply by 13 kilowatt hours per kilogram of aluminum, I get this astronomical number of 5.3 times 10 to the 11th kilowatt hours. And you might say, well, that looks like a big number, but I'm not sure what it means. It turns out that that's about 2% of all the electrical energy generated in the entire world every year. So at a typical household rate of about 12 cents per kilowatt hour, if you were the one paying for this electricity to produce aluminum, your bill would be about $64 billion. So once again, we say recycle aluminum wherever possible.